next speaker is Matteo RISSO from the Politecnico di Torino. It's on pruning in time, a lightweight network architecture optimizer for temporal convolutional networks. Matteo, please take over.
Good afternoon, and thank you for the introduction. And as said in the title, this work deals mainly with the temporal convolutional networks and their optimization. But why we want to do this? Let's say that existing works focus mainly on 2D convolutional neural networks for computer vision tasks, but the vast majority of edge-relevant tasks are unidimensional, and temporal convolutional networks represent a unidimensional flavor of convolutional neural networks particularly well suited for time series processing tasks. Here, in this snapshot, we can see an example of temporal convolution, which is basically a normal convolution with two additional features, which are the causality, which means that data are processed from left to the right following the arrow of time, and dilated convolution, which we can appreciate here. We can see that the kernel, the convolutional kernel, it is not convolved on contiguous samples, but the samples are equally spaced across the time domain, and this allows us to enlarge the receptive field without increasing the number of weights. Moreover, no state-of-the-art approach analyzes architecture search for unidimensional neural networks at the edge, and for this reason, we propose an approach based on differentiable neural architecture search, DNAS. Here, the basic DNAS flow is proposed, and in few words, we can say that in the same training loop, we are able to train normal weights as well as some additional parameters which encodes for different architectural configuration. And let's go to our method, PIT, which is an acronym that stands for pruning in time, which is a DNAS algorithm that learns the optimal dilation factor of each convolutional layer in a certain seed architecture. And this approach is orthogonal to other DNAS approaches, which usually targets the search of the optimal number of channels and or the kernel size of each convolutional layer. As said, we start from a seed network and a certain input dataset, and in the context of our algorithm, we basically couple the normal kernel tensor K with an additional binary trainable mask gamma. This mask gamma encodes the different dilation factor that we want to explore in our search. Then the pointwise multiplication of the two is performed, and the resulting kernel is used to replace the normal one in the basic architecture. Then the architecture, it is inserted in a normal training loop where we can train at the same time the normal weights K as well as the gamma parameters. Let's end with a few results based on the PPG-based heart rate monitoring task on the PPG DALIA dataset and the TempoNet architecture, which is a state-of-the-art TCN. With our algorithm, we obtain various Pareto-optimal architectures, here summarized, and we span a search space of about 10 to 4 alternatives, and we are also able to compress and improve at the same time the seed network. Moreover, we propose a comparison with a state-of-the-art DNAS approach, which is proxyless NAS. Proxyless NAS, what basically perform is putting layers in parallel, and during the search process, we choose layers among these one. And we tweak proxyless NAS to perform the same search as our algorithm, and we find that our method is much more faster. In fact, we are able to achieve a speed up in the training time up to 10.4 times. This is the end, and thank you for the attention.
Thank you very much. Let me see. I think that there is one question on the Q&A. An attendee is asking us where they can read more about this approach, whether there is a paper published or.
Yeah, this work will be presented at the DAC in the upcoming DAC 21 conference. Then, if you follow me on Scholar, you will see appear the paper in the upcoming days, let's say. Moreover, also the code will be open sourced. Then it is only a matter of waiting. Then for whatever you can ask me at my email, which is written here, and I will give you all the information. Thank you.
There is another question by Christoph that I see here. Does the 1D points to the time series? And what about the SFTF?
Can you repeat the question, please?
The question is, does the 1D, I guess, points to the time series itself? And then, and then there is an acronym about the SFTF there.
Yes, I think this is short Fourier transform, but the signal used are raw, completely raw. Then they represent the input samples gathered from a sensor. In particular, in the benchmark task, which is PPG-based heart rate monitoring, we use a PPG sensor plus an accelerometer in order to track in a reliable manner the heart rate of the subject. Which, in particular, the application, it is based on wearable devices, and then we want to track the heart rate of the subject wearing the smartwatch. But the signals are completely raw. Then no short Fourier transform or any other feature extraction techniques.
Okay, thank you, Matteo.
I want to thank our sponsors that made this event possible. So the premier sponsors, Newton, working on automated TinyML. If you were there a few days ago, they had a keynote explaining what they're doing. Executive sponsors are ARM, Edge Impulse as well, and Qualcomm. Sentient, and then our platinum sponsors, we have Infineon and Reality AI. Gold sponsors are Latent AI, SensiML, and our silver sponsors are EMEA, Greenwaves, HOTG, Imagimop, GISO, SEED, and ST. And with that, I thank you very much for staying on till the very last end, the last day of the last session of the last day. And with that, I think we can close the forum for this year. Thank you, everybody, for contributing. Thank you, Andreas, for also moderating this session.